Welcome to all of you. Now we discuss Unit 2 2023 Biomathematics, Semester 5 CBCS Mathematics Honors, University of Calcutta. Question paper 2023 Biomathematics, Unit 2, Group B Unit 2, Question 4a. Linearize the classical Lotka-volterra model dDtx equal to alpha x equal to beta xy, dDty equal to minus gamma y plus delta xy about the positive steady state where alpha, beta, gamma, delta are positive parameters, hence so that both prey and predator have periodic solutions with same period. Now we have the given system, right? Dt of x equals to fxy and dt of y equal to gxy, where fxy equal to alpha x minus beta xy and gxy equal to minus gamma y plus delta xy. For steady state x star y star, we have f of x star y star equal to 0 equal to g of x star y star. So obviously, this x star bracket alpha minus beta y. Actually, you can write this for steady state. For steady state, for steady states, we have delete this star fx fxy equal to 0 and gxy equal to 0. So for steady state, we have fxy equal to 0, gxy equal to 0. Then this alpha x minus beta xy equal to 0. So taking common x into bracket alpha minus beta y equal to 0. So either x equal to 0 or y equal to either x equal to 0 or y equal to alpha y beta. And from gxy equal to 0, we get this taking y common into bracket minus gamma plus delta x equal to 0. So either y equal to 0 or x equal to gamma y delta. So for a positive steady state, actually, if you choose x equal to 0 from this first equation, next you can choose y equal to 0 from the second equation. And if you choose x equal to gamma by delta from this second equations, and you must choose this y equal to alpha by beta. So non-positive steady state, this x star y star equal to x equal to gamma by delta comma alpha by beta. Because in this question, this positive steady state, about the positive steady state. So we consider here only positive steady state, not trivial steady state. Let us write this u and v. It is equal to x minus x star and v equal to y minus y star. Here, this u is part of perturbation, small perturbation, and v equal to small perturbation about x star and y star respectively. Then linearized system about x star y star, this positive steady state, is given by dt of u equal to fx, that is del f del x at the point x star y star into u plus del f del y at the point x star y star into v. And ddt of v equal to del g del x at the point x star y star into u plus del g del y at the point x star y star into v. And this from the theory of two uh, variables, we can easily derive this linearized system. Now del f del x this equal to alpha minus beta y because f equal to this alpha x minus beta xy, so del f del x equal to alpha minus beta y, and del f del y equal to minus beta x, del g del y del g del x equal to delta y, del g del y equal to minus gamma plus delta x. So del f del x at the point x star y star, put this value of y equal to alpha by beta. So put here alpha by beta, so beta beta cancel, so alpha minus alpha equal to 0. Del f del y at the point x star y star, this minus beta x star, and value of x star is gamma y delta, so this equal to minus beta gamma y delta. And so del g del x at the point x star y star is equal to alpha delta by beta, and del g del y x star y star equal to 0. Hence, the system linear system 1 becomes du dt equal to minus beta gamma by delta v, and dv dt equal to alpha delta beta into u, equation 2 and 3 respectively. Differentiating 2 with respect to t, time variable t, we get d2u dt square equal to minus beta gamma by delta and dv dt. And the value of dv dt from 3 is alpha delta by beta into u. So d2u dt square equal to minus beta beta cancel, delta delta cancel, so minus alpha gamma into u. Clearly, this equation 4 represents a simple harmonic motion, that is simple harmonic oscillator with frequency root over alpha gamma by 2 pi. Hence, pre here pre stands for u, that is x, variable x, pre has a periodic behavior with period of oscillation 2 pi by root over alpha gamma. Or note that d2x dt square equal to minus omega square x. This is a simple harmonic motion. Here omega is the angular frequency, this is equal to 2 pi f. F is the frequency, this is equal to omega by 2 pi, and t is the time period, that is period of oscillation, is equal to 1 by f, is equal to 2 pi by omega. So by using this simple harmonic motion equation, you can easily derive this frequency and this period of oscillation. And similarly, from 3, differentiating with respect to t, and we get d2v dt square equal to minus alpha gamma v. And this is also a simple harmonic oscillator, and for predator here v, that is for y, with period of oscillation 2 pi by root over alpha into gamma. Next question, question 4b. Investigate the stability of the non-trivial steady states of the following competition model. Dx dt equal to x into bracket 16 minus 2x minus y, and dy dt equal to y bracket 12 minus x minus y. Let dx dt equal to fxy and dy dt equal to gxy, where fxy equal to x into bracket 16 minus 2x minus y, and gxy equal to y into bracket 12 minus x minus y. For steady states, ddt of x equal to 0 equal to ddt of y. Hence, this x into bracket 16 minus 2x minus y equal to 0. So either x equal to 0 or 2x plus y equal to 16. And from gxy equal to 0, we get y either y equal to 0 or this x plus y equal to 12. If we choose x equal to 0 from equation 1, then we can choose y equal to 0 or x plus y equal to 12. So if we choose y equal to 0, then this steady states 0, 0. And if we choose x equal to 0 and x plus y equal to 12, so y equal to 12. So we get, for this x equal to 0, we get 0, 0 or 0, comma 12. And if we choose y equal to 0 from this second equation, and then from equation 1, so we get this x equal to 0. So this is 0, 0. And this from this y equal to 0. So put here y equal to 0. 2x equal to 16, that x equal to 8. Already we get this 0, 0. So here we can take this steady state 8, comma 0. Next, solving this 2x plus y equal to 16 and x plus y equal to 12, and we get this positive steady state, this x equal to 4 and 8. So there are 4 states: 0, 0, 0, 12, 8, 0, 4, 8. 0 is the trivial steady states, and other 3 are non-trivial steady states. The question is, investigate the stability of the non-trivial steady states. So for this, first we find this Jacobian or variational matrix. For that we find fx, fy, gx, and gy. And Jacobian G equal to this matrix 2 by 2 matrix fx, fy, gx, gy. So this. So for this point, first we investigate for this point, non-trivial steady state 0, 12. So put x equal to 0 in this matrix and y equal to 12. So we get this 2 by 2 matrix 4, 0, minus 12, minus 12. And this is a lower triangular matrix. So eigenvalues the diagonal elements 4 and minus 12. And this 4 is positive and this minus 12 negative. So for this positive eigenvalues, obviously this steady state 0, 12 is an unstable steady state. Next, for the points steady state 8, 0. So value of Jacobian at the point 8, 0, we get minus 16, minus 8, 0, 4. This is an upper triangular matrix. So the eigenvalues are the principal diagonal elements. So this minus 16 and 4, and this 4 is positive eigenvalue. So this steady state also 8, 0 is also an unstable steady state. Next, for this steady state 4, 8, and Jacobian J at the point 4, 8, we get minus 8, minus 4, minus 8, minus 8. And for this, we use Routh-Hardy criterion. And so we can find trace of J. Trace of J is the sum of these principal diagonal elements, minus 8, minus 8. This is equal to minus 16, and this less than 0. And determinant of this J, this is equal to 32, this positive. So by Routh-Hardy criterion, the steady state 4, 8 is locally asymptotically stable. You can find eigenvalues by characteristics equation and so on, so on, so on. But it is easy to find this by Routh-Hardy criterion to find whether the steady state is locally asymptotically stable or not. Next question, question 5. Discuss the stability of the steady states of the following predator-prey system: dx dt equal to x bracket 1 minus x by 30 bracket close minus xy whole divided by x plus 10, and second equation dy dt equal to minus 3y by 5 plus xy whole divided by x plus 10. This marks is 10. Put marks 10 for this question. is subdivision of this mark 1 plus 1 plus 2. Find the steady states and the analysis of the steady states 2 plus 2 plus 2. First we write dx dt equal to fxy, dy dt equal to gxy, where fxy equal to this function and gxy equal to this function. And for steady states, we know this dx dt equal to 0 and dy dt equal to 0. So from this, we get this equal to 0 implies either x equal to 0 or this actually factorize. You can factorize this. And this actually 1 minus x by 30 equal to y by x plus 10. So y equal to 1 minus x by 30 into x plus 10. And from this dy dt equal to 0, this minus 3y by 5 plus xy by x by 10 equal to 0. So taking y common, so we get either y equal to 0 or solving this factor, we get x equal to 50. So if we choose x equal to 0 from this first equations, then you can choose this y equal to 0 from the second. So 0, 0 is in steady state. If we choose x equal to 0, then x equal to 0, not x equal to 15. So only this x equal to 0 and y equal to 0. And if we choose x equal to 15 from this second system, then from so you must choose this from first system, this y equal to this. So put x equal to 15 here. So y equal to 25 by 2. And if we take y equal to 0 from this system 2, and this put here y equal to 0, and then from 2, and then we get this x plus 10, y equal to 0. So x plus 10 into 1 minus x by 30 equal to 0. So x equal to minus 10 or x equal to 30. But uh, for visible solution, x cannot be negative or 0. This x must be positive. So we choose here non-negative restriction for x is x equal to 30. So neglecting x equal to minus 10, we get xy is steady state 30, 0. So there are three steady states, this 0, 0, 30, 0, and 15, 25 by 2. Next, we find the Jacobian J. For that, we calculate fx del f del x. So this is equal to 1 minus x by 15 minus 10y by whole divided by x plus 10 whole square. And del f del y, this is equal to minus x by x plus 10. Del g del x, this is equal to 10y whole divided by x plus 10 whole square. Del g del y equal to x by x plus 10 minus 3 by 5. And then Jacobian J equal to fx fy gx gy 2 by 2 matrix. So we get this Jacobian case. Now stability analysis for the first steady state 0, 0. So put x equal to 0, y equal to 0 in this Jacobian. So we get 1, 0, 0 minus 3 by 5. So obviously this diagonal matrix, so eigenvalues are 1 and minus 3 by 5. And because this eigenvalue positive, so this trivial steady state is an unstable steady state. Next, for the steady state 30, 0, find the value of j at this point. So you get this, put x equal to 30 and y equal to 0. So you get this minus 1 minus 3 by 4, 0, 3 by 20. Obviously, this is an upper triangular matrix. So eigenvalues are the diagonal, principal diagonal elements, this minus 1 and 3 by 20. And because this 3 by 20 eigenvalue is positive, so this steady state 30, 0 is also an unstable steady state. Next, for this positive steady state 15, 25 by 2, and value of j at this point is minus 1 by 5, minus 3 by 5, 1 by 5, and 0. So here we find trace of j, that is the sum of the principal diagonal elements is equal to minus 5, this negative, and determinant of this j, so this is equal to 3 by 25, this positive. So by Routh-Hurwitz criterion, this is an asymptotically stable steady state. Next question 6. Consider the following model of bacterial growth in a chemostat, dNdt equal to K1C by K2 plus C bracket n minus Fn by V, and dCdt is equal to minus alpha bracket K1C by divided by K2 plus C into n minus Fc by V plus Fc0 by V, where the symbols have their usual meanings. Question A, so that the equations can be reduced to the following dimensionless form by the substitution n equal to fk2 by alpha vk1 into u and c equal to k2v and p equal to v by f into tau. This non-dimensional equation, this du d tau equal to alpha 1 bracket v by 1 plus v into u minus u, and dv d tau equal to minus v by 1 plus v into u minus v plus alpha 2, where alpha 1 alpha 2 are the parameters determined by u. Question B, find the steady states of the dimensional system. Find the conditions on alpha 1 and alpha 2 so that the steady states become biologically meaningful. Question C, determine the stability of the biologically meaningful steady states. Number distribution is 2 plus 3 plus 5. Now, this variable n equal to fk2 by alpha v k1 into u. So, differentiating with respect to t, so dndt equal to fk2 alpha v k1, this du dt, but you can write by chain rule du d tau into d tau dt. Now t equal to v by f into tau. So obviously, d tau dt equal to f by v. So put here d tau dt equal to f by v. So dn dt equal to f k2 alpha v k1 f by v du d tau. Hence, this first equation, this dt of n equal to k1c divided by k2 plus c into n minus fn by v becomes, put this value of dn dt from this equal to k1, this value of c is this k2 into v. So put here k2 into v and c equal to k2 into v, and value of n is this f k2 by alpha v k1 into u minus f by v, and value of n equal to this. So after simplification, we get this du d tau equal to alpha 1 v by 1 plus v into u minus u. Clearly, this alpha 1 equal to v k1 by f, this parameter alpha 1. Next, we have c equal to k2 into v. Differentiating with respect to t, so dc dt equal to k2 dv dt by chain rule dv d tau into d tau dt. So k2 d tau dt equal to f by v. Already we get this f by v. So this is equal to f by v into dv d tau. Hence, this second equation, dt of c equal to minus alpha k1c by k2c into n minus fc by v plus fc0 by v becomes, value of dt of c is this, and minus alpha k1, value of c is k2v, c is k2v, and value of n is this, f by v, value of c is k2v, f by v into c0. And after simplification, we get d tau of v equal to minus v by 1 plus v into u minus v plus alpha 2. Actually, this alpha 2 equal to this c0 by k2. c0 by k2, this is the alpha 2. Since the parameters c0, a, v, k1, k2, alpha are all positive, then alpha and alpha 2 are also positive. And this equation 1 and 2, this equation 1 and this equation 2 are the required dimensionless form of the given system. Next question B. Find the steady states of the dimensionless system and find the conditions on alpha 1, alpha 2 so that the steady states become biologically meaningful. So this let du d tau equal to f of u comma v. and uh, dd tau of v equal to g u comma v, where if u v equal to alpha 1 v by 1 plus v into u minus u, and g u v equal to minus v into 1 v into u by 1 plus v minus v plus alpha 2. For steady states, we have du d tau equal to 0 equal to dv d tau. So this taking common u, so either u equal to 0 or this alpha 1 v by 1 plus v equal to 1. And from this dv d tau equal to 0, we get this equation 4. If we choose u equal to 0, then from 3 we get v equal to alpha 2. V equal to alpha 2, then from 3, no, then from 4. Then from 4, we get this, put u equal to 0 here, so v equal to alpha 2. So this steady state uv is equal to 0 comma alpha 2. Next, now alpha 1 v by 1 plus v equal to 1 from this system 3. So alpha 1 equal to 1 plus v by v. This implies alpha 1 equal to 1 plus 1 by v is equal to v equal to 1 by alpha 1 minus 1. Alpha 1 minus 1. Then from C, put this, from C we get this v plus v by 1 plus v into equal to alpha 2 from 4. And put the value of v, this is equal to 1 by alpha 1 minus 1. And this v by 1 plus v, v plus 1 by v equal to 1 by alpha 1 from this. So put 1 by alpha 1 into u equal to alpha 2. So from this, after simplification, we get u equal to bracket alpha 2 minus 1 by alpha 1 minus 1 into alpha 1. So alpha 1 into alpha 2 minus alpha 1 by alpha 1 minus 1. So v equal to, when v equal to this and u equal to this. So another steady state, this u comma v, this equal to alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1 comma 1 by alpha 1 minus 1. And thus we get two steady states, this u1 star comma v1 star say equal to 0 comma alpha 2. Already we get this 0 comma alpha 2, and u2 star comma v2 star equal to this alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1 comma 1 by alpha 1 minus 1. Clearly 0 comma alpha 2, this steady state is feasible, that is biologically meaningful, because this alpha 2 always positive parameter, so this non-negative, this both are non-negative, so this is feasible. But u2 star v2 star is feasible, biologically meaningful, if alpha 1 minus 1 greater than 0, that is alpha 1 greater than 1, and if alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1 greater than 0, that is if alpha 2 greater than 1 by alpha 1 minus 1. Taking common alpha 1, this alpha 1 greater than 1. So this actually this obviously alpha 2 greater than 1 by alpha 1 minus 1, and alpha 1 greater than 1 for feasibility of u2 star and v2 star. We're taking common alpha 1, this alpha 1 greater than 0, so cancel this. Next, question C. Question C, determine the stability of biologically meaningful steady state. For this, we find the Jacobian J u comma v. So f equal to this, g equal to this, del f del u, find this del f del v, del g del u, and del g del v. Hence Jacobian J equal to f u f v g u g v. This equal to this alpha 1 v by 1 plus v minus 1, alpha 1 u by 1 plus v whole square, and this minus v by 1 plus v minus u by 1 plus v whole square minus 1. Now stability analysis for this steady state 0 comma alpha 2, and this put u equal to 0 and v equal to alpha 2 in this Jacobian 2 by 2 matrix. So we get this, and this is a lower triangular matrix obviously. So its eigenvalues are the diagonal elements, this -1 and this alpha 1, alpha 2 by 1 plus alpha 2 minus 1. And if the minus 1 is negative, so if this eigenvalue is negative, that is if alpha 1, alpha 2 by 1 plus alpha 2 minus 1 is less than 0, that is if alpha 1 by 1 plus alpha 2 less than 1, that is alpha 2 common, this bracket alpha 1 minus 1 is less than 1, that is alpha 2 is less than 1 by alpha 1 minus 1, alpha 2 is less than this. So alpha 2, when alpha 2 greater than 1 by alpha 1 minus 1, then this U2 star V2 star is feasible. If alpha 2 less than 1 by alpha 1 minus 1, this is unfeasible because not exist, does not exist this U2 star V2 star. So we get this condition is this stable, this alpha 0 comma alpha 2 asymptotically stable if this condition alpha 2 less than 1 by alpha 1 minus 1. This alpha 2 less than 1 by alpha 1 minus 1 and unstable otherwise. That means this 0 comma alpha 2 steady state unstable when alpha 2 greater than 1 by alpha 1 minus 1. Also note that if alpha 2 less than 1 by alpha 1 minus 1, U2 star V2 star is unfeasible. That is does not exist this. Next steady state, this U2 star V2 star. So this alpha 1 alpha 2 minus alpha 1 by 1 alpha 1 minus 1 comma 1 by alpha 1 minus 1. And this feasible that is exist when alpha 2 greater than 1 by alpha 1 minus 1 and alpha 1 greater than 1. That is alpha 1 alpha 2 minus alpha 2 minus 1 is greater than 0 and alpha 1 minus 1 greater than 0. Now we find Jacobian J at this point U2 star and V2 star. Put U2 star equal to this and V2 star equal to this. In this Jacobian, this there is value of U and V replaced by this value. And after simplification, we get this 2 by 2 matrix 0 bracket alpha 1 alpha 2 minus alpha 2 minus 1 bracket into alpha 1 minus 1 and this minus 1 by alpha 1 and this minus 1 minus bracket alpha 1 alpha 2 minus alpha 2 minus 1 into bracket alpha 1 minus 1 by alpha 1. Now this trace of this element the matrix, this 0 plus this, so this quantity, this minus 1, this minus, and obviously alpha 1 minus 1 greater than 0 because this U2 star V2 star is feasible and this alpha 1 minus 1 greater than 0 and alpha 1 alpha 2 minus alpha 2 minus 1 is also greater than 0 for existence of this U2 star V2 star. So obviously both are positive and alpha 1 is also positive. So obviously this trace is negative and determinant of this Jacobian this we get 1 by alpha 1 alpha 2 minus alpha 2 minus 1 into bracket alpha 1 minus 1. Obviously this is 0 because this is positive and this is positive and alpha 1 is positive. So determinant of this Jacobian at this point U2 star V2 star is positive. Hence by Routh-Hurwitz criterion U2 star V2 star is asymptotically stable when alpha 1 alpha 2 minus alpha 2 minus 1 is greater than 0 and alpha 1 minus 1 is greater than 0. Next question, question 7a. So that the following system ddt of x equal to minus y plus x into bracket 1 minus x square minus y square, and second equation ddt of y equal to x plus y bracket 1 plus minus x square minus y square has a stable limit cycle. Now the corresponding linear system, and because the given system is nonlinear because x square y square term, so corresponding linear system is ddt of x equal to minus y plus x and ddt of y equal to x plus y. And for equilibrium point x star y star, we have ddt of x equal to 0 equal to ddt of y at this point x star y star. Now, this x star y star equal to 0, comma 0, that is the origin, is the critical point or equilibrium point of the linear system as well as the given nonlinear system. Hence, this equation 1, system 1, it can be written as in the matrix form x dot y dot, actually column matrix. X dot means ddt of x and y dot means ddt of y. This x1, 1 minus 1, 1, 1, xy. And the characteristic equation, this 1 minus lambda minus 1, determinant of this 1, 1 minus lambda. So lambda equal to 1 plus minus I, where I square equal to minus 1. Eigenvalues are 1 plus minus I. Since real lambda, this is 1 greater than 0, the origin critical point 0, 0 is an unstable spiral point for both the linear and nonlinear system. Next, we study the given system. For that, we introduce the polar coordinates r theta. We choose x equal to r cos theta, y equal to r sin theta. Now, x dx dt plus y dy dt equal to x, this value of dx dt from the given equation, this dx dt equal to minus y plus x bracket 1 minus e square minus y square plus y dy dt from the given equation x plus y into bracket 1 minus x square minus y square. After simplification, we get this 1 minus r square into r square, because r square equal to x square plus y square. Now r square equal to x square plus y square, differentiating t with respect to 2r dr dt equal to 2x dx dt plus 2y dy dt. Hence, cancel 2 from both sides. So this x dx dt plus y dy dt, this we can replace by this r dr dt. So r dr dt equal to this r square 1 minus r square. And since this r is not equal to 0, because this meaningless of this system, so r not equal to 0, we get ddt of r equal to r into bracket 1 minus r square. So this is the first equation of the given system. And next, y ddt of x minus x ddt of y is equals to y from the given equation this, and minus x into from the given equation dx dt dy dt equal to this. After simplification, we get minus r square. Now, dx dt equal to minus r sin theta d theta dt, and dy dt equal to r cos theta d theta dt. So y dx dt minus x dy dt equal to value of y equal to r sin theta and dx dt equal to minus r sin theta d theta dt, and this y minus x equal to r cos theta and dy dt equal to r cos theta d theta dt. So after simplification, we get minus r square d theta dt. So from this, y dx dt minus x dy dt equal to minus r square d theta dt. So we can replace this minus r square d theta dt equal to minus r square. So cancel from both sides, d theta dt equal to 1. Hence, the in polar coordinate system, the given system, nonlinear system, becomes ddt of r equal to r into bracket 1 minus r square, and ddt of theta equal to 1. This is the uh, given corresponding nonlinear system in polar coordinates. Now, let f r equal to r into bracket 1 minus r square. So f dash r equal to 1 minus 3r square, r into r cube, so minus r cube, so 3r square. Now, if r equal to 0 implies r equal to 0, r equal to plus minus 1, but r is positive, so we take only r equal to 1. So, if dash at this point r equal to 0 is equal to 1, this 1, and if dash 1, this 1, put here 1, is equal to minus 2, so f dash 1 is negative. So from this uh, um, stability analysis for one dimension, this r axis r is the dr dt. If I portray this, so this curve is r into bracket 1 minus r square. So this point 0 and this 1. So clearly r star equal to 0 and r star equal to 1 to steady state here. And obviously here this arrow from origin, and this for this point 1, this towards this 1. So this is negative, f dash 1 is negative. So this is the stable solid circle at this point, in this hollow circle, this at this point unstable steady state. So r star equal to 0 is an unstable steady state, and this 1 is the stable steady state. Now we observe that dr dt is positive for 0 less than or less than 1. So dr dt is positive. Actually, this is the FR is the DRDT. So here curve is here. So this is the positive. This is the positive from between this, and DRDT equal to 0 at this point 1, and DRDT negative when R is greater than 1. So this is the negative. Thus, trajectories inside R equal to 1, R equal to 1, R equal to 1 means uh, R, R square equal to X square plus Y square. So actually R square equal to 1, this is the unit circle with a circle center at origin. Move out, move out to R equal to 1. Trajectory inside, because inside means when 0 less than R less than 1. Because dr positive, so dr positive means move out. Dr positive means move out to R equal to 1. And from this, figure this, R equal to 1 is this circle, R equal to 1. So when R is the distance from the origin. So when R 0 less than R less than 1, when 0 less than R less than 1, dRdt positive. So dRdt positive means dRdt means velocity. So this trajectory move out from origin towards this circle R equal to 1. And when R equal to 1, R equal to 1, that is from on this trajectory, this dRdt equal to 0. So uh, trajectory stay on R equal to 1 all time, for all time. And when R is greater than 1, that is the outside trajectory, dRdt negative. dRdt negative means velocity negative, this towards this. So from this outside, this towards this R equal to 1. So except for the steady state at the origin, trajectories move towards the circle R equal to 1. Since d theta dt equal to 1, all trajectories travel counterclockwise at a constant rate. This is the d theta dt is the uh, angular velocity. This counterclockwise, this plus 1 for this plus 1, and for this minus 1 is the clockwise sense. So this is the counterclockwise rotation for this trajectory rotation in counterclockwise sense. Since dRdt equal to 0 at R equal to 1, we see that R equal to 1 is the periodic trajectory. So of all times, this trajectory when R equal to 1, all times the periodic trajectory is R equal to 1. Since nearby trajectories converge to the circle R equal to 1, so from outside, from both inside and from outside, we conclude that circle R equal to 1, unit circle uh, with radius 1 at the origin, central origin, is a stable limit cycle. Is a stable limit cycle. This is the diagram for this stable limit cycle. Next question. State the basic assumptions of the Carmack-McEnrick SIR model, draw the flowchart, and write the model equations. Find the basic reproduction number distribution 2 plus 2 plus 1. Basic assumptions for this Carmack-McEnrick SIR model. In this model of infectious diseases, the population is assigned to three compartments or classes with labels S, I, and R. Here, ST denote the number of individuals who are susceptible to the disease, and I denotes the number of infected individuals, and RT denotes the number of recovered individuals at time T. The first assumption is that the gain of I is at a rate of proportional to the number of I, that is beta S into I, where beta greater than 0 is the infection rate. The loss of S is also at the same rate, that is beta Si. Second assumption, the rate of removal of I to R is proportional to I, that is gamma I. Here gamma is positive, is the recovery rate. Third assumption, the incubation period, that is the time interval for which disease remains in a dormant or latent state within body, is short enough to be negligible. That is, a susceptible who contracts the disease is infective right away. Fourth assumption, the various classes are uniformly mixed. That is, S, I, and R, these compartments are uniformly mixed. Assumption 5, this recovered, that is R, has no possibility of infected again or spreading infection. Removal is carried out through isolation from the rest of the population and through immunization against infection, through recovery from the disease with full immunity against reinfection, or through death caused by the disease. So for this model, we this chart, this flow chart is this is susceptible, this from outer arrow to I, this beta Si, and from this infected to outer arrow, this the recover this gamma I. And Karbeck-Mechanic model equations are this, ddt of S equal to minus beta Si and didt equal to this input this, so plus beta Si, and output is this minus gamma I. And for this ddt of R, this is equal to gamma I, this is the input, only this. Now we want to find the basic reproduction number for this model. Initially at time t equal to 0, this S at the point t equal to 0, we say this equal to S0, this positive. I0 infected at this time t equal to 0, I0 positive, and initially recover equal to 0, obviously. Now ddt of S equal to minus beta Si, beta is positive, S and I are positive, so obviously this is negative for all time t greater than 0. This implies DSDT less than negative, so obviously S is a decreasing function of t. S is a decreasing function of t. Actually, this S is a decreasing function of t. This is curve of S, this decreasing function of t. This time, x-axis is time, and this is the population. So S is decreasing function of t. Next, note that S and I remain non-negative for feasibility of the model, not equal to 0. Now, didt equal to beta I bracket S minus gamma by beta. Because this taking common beta I, so beta I S minus gamma by beta. This greater than 0 if and only if this S minus gamma by beta greater than 0, that is S is greater than gamma by beta. This implies I increases this I, this infected, this graph is I increases for this time, so long S greater than gamma by beta. So long S greater than gamma by beta. But since S decreases for all t, so I ultimately decreases and approaches to 0. Yes, so ultimately decreases and approaches to 0 because S is decreasing function. Now take the case 1, two cases. Case 1, if S0 initial value of S at this point is less than gamma by beta. So S0 equal to S0. So I decreases to 0. That is, there is no epidemic when S0 less than gamma beta. That is if beta S0 by gamma is less than 1. That is if R0 is less than 1. We say this R0 equal to beta S0 by gamma. This R0 called this basic reproduction number. So when R0 is less than 1, then there is no epidemic. Now, if S0 initial value of S is greater than gamma by beta, I first increases, so I first increases to this, and ultimately is decreasing function. So then there is an epidemic for this. When increases, so I infected increases, so there is an epidemic, and then decreases to 0. Then I decreases to 0. If S0 greater than gamma by beta, that is if beta S0 by gamma greater than 1, that is if R0 greater than 1, and this an epidemic occurs. The quantity R0 equal to beta S0 by gamma is a threshold quantity which is known as the basic reproduction number. It is the number of secondary infections produced by one primary infection in a wholly susceptible population. This completes the Unit 3 2023. Thank you for watching this video.